And then we are going to try to come back to the implicit function theorem today, which we started a week ago. We started motivating it a week ago. And so today we're going to write down our big conjecture as to the theorem we thought we could prove, and then we're going to try to prove it. If this should be a lot less painful than proving the inverse function theorem. So we'll go through the proof, and then we'll try to do one or two examples to see what we can actually do with this theorem. So let me write out the theorem first of all. And again, we talked about this a week ago, or a little over a week ago maybe. Everything in here we tried really hard to motivate with simple examples, either low dimensional or linear, and some nice pictures to go along with it. And now we're going to see how we can prove this. So let us suppose that we have some mapping, and it's not square, so we have more inputs than outputs. But it's kind of well behaved. It is continuously differentiable. Okay, on some open set. And we have some reference point. I think the focus is changing here. Let's see. See if that helps. We have some reference point that lives inside our open set. Okay, so what was true about this reference point? Well, what we were trying to do, we're trying to solve f equals 0. So we'd found one point on the surface, and we're trying to identify other points that are on this surface, f equals 0. So we're going to suppose also that f of x naught and u naught is equal to 0. And we decided that the thing that we probably needed here in order to be able to do what we want to do, and what are we trying to do? We're trying to identify other points in the surface. We can't solve for all of them. We have a mismatch between the number of equations and the number of unknowns. So what we hoped we could do is solve for all these u variables in terms of the x variables. Because when we split this up, we said n refers to the number of x variables, m to the number of u variables, and m is also the number of outputs we have here. Okay, so we said in order to do this, we thought that probably we would need the Jacobian with respect to the u variables to be invertible. Okay, so then these were the hypotheses we thought that were probably reasonable. And then the conclusion we made was that there exists some neighborhood of our reference point okay, on which what? On which, well, the Jacobian continues to be non-singular. There's not much to prove there. The Jacobian is continuous because we've assumed that f is continuously differentiable. So if it's invertible at this point, it will be invertible of a neighborhood of that point. Okay, so I'm not really saying much here. And then the important thing was that actually we could find a neighborhood of x naught on which we could actually find a way to solve for the u's in terms of the x's. So we said, and there's a neighborhood n of x naught on which we can identify the kind of function we're looking for. So on which there is a what? I'm going to kind of maybe bullet point the things we want to prove. There's going to be kind of a list of things that we want to prove, and they're all going to be very short little proofs. So we would like to show that there is a unique and continuously differentiable function, g. G is the function that lets us solve for the u's in terms of the x's. So what is g? G takes as inputs the x variables. The x variables live in Rn. Okay, and it spits out our u variables. The u variables live in Rm. And what are some other properties we want to see here? Well, we want to see this matches with our reference point. At our reference point, we get back what we expect. Okay, we expected these points, this collection of points, x and g of x, right? So normally our points are x, u. Now the u's are given by g of x. We expect them to stay close by to our reference point. So the way we stated that was that this collection of points, the x and u's that we're going to solve for, are going to stay in this neighborhood of our reference point. And this is going to be true as long as our x's stay in their appropriate neighborhood. And then the biggest thing that we wanted, the whole goal was we're trying to solve f equals 0. This function is going to do that for us. If we plug in x and then we replace u by this g of x function, indeed we're going to get 0. Okay, and better than that, we could also say something about the Jacobian of this function g, right? We know we're probably not going to write down g explicitly, but we can say something about, well, we know what happens to it at a reference point. We're going to be able to write down its Jacobian and find that that's very easy to compute, at least at this reference point. And that means that it's open to us to do a linearization, because we know that if this part is true, g is continuously differentiable, then locally it's going to look a lot like its linearization. So last point is that the Jacobian of g is equal to, now this is the formula that we got by looking at the linear case, and it also agreed with the formula that we got when we did the low dimensional case. So we're going to try it out. So we said it was minus the inverse of the u Jacobian, right? And this we know is perfectly well defined, okay, because we said that the u Jacobian is invertible. So there's no problem writing this down. And then times the x Jacobian. Okay, so this is what we want to prove. It looks like a beast, but I think that we're going to find that it's not too bad, actually. Any questions before I jump onto the proof? As always, feel free to jump in and ask questions. I also have the chat window open in front of me, so I try to pay attention to anything that shows up there. Okay, so what's the plan for the proof? The plan for the proof is that we don't want to have to do any more work than is absolutely necessary. Sometimes much work is necessary, but we know that we've a couple weeks ago proved a theorem that has a similar flavor to this. It's the same. This is more complicated, definitely, but the inverse function theorem somehow had a similar flavor, that we have this mapping that's nice. It's continuously differentiable. We've got a Jacobian that's non-singular, and all of a sudden we can compute this inverse function, which I think we call g, that somehow does something. So what we'd like to do is really take this problem and rewrite this problem as an inverse function theorem problem, and then use the result that we already have. Okay, so this is our approach. Let's start the proof. And we want to do something with the inverse function theorem. Well, one thing we definitely need for that is we need a square mapping, which we don't currently have. So right now, what do we have? We have a function that takes, all right, we have too many variables being mapped onto not enough equations. So we've got to somehow extend this to have the correct matching between the number of inputs and the number of outputs. So let's just, to take an example, suppose that I have a function depends on x, u1 and u2. Okay, so 3 inputs, but only 2 outputs. Now, if I'm going to have 3 inputs, what I really need is 3 outputs, so we have to somehow extend this to a new function. So somehow I want to build some new function, and I'm going to call phi, that has 3 inputs, but also 3 outputs. Okay, so we need, in this example, we need 1 extra input. In general, we'll need n extra inputs. So the number we have a number of equations that corresponds to these guys. These are u1 squared and u2 squared in this case, so probably we should leave those alone because, you know, we still want to be saying something about this function at the end of the day. But we need to put something here. Any suggestions for what would be convenient to put there? Okay, Gabriel suggested 0. That's a natural thing maybe to try. We want to do something simple. So you're on the right track in that you want to do something simple. Let me make another suggestion. What are some of the properties that we want phi to satisfy? Remember, what do I want to do? I want to do inverse function theorem on this guy. So what's the really important thing that needs to be true if I'm going to be able to use the inverse function theorem? There's one really key hypothesis. We can go back to the implicit function theorem, which has a very similar important hypothesis. A non-zero determinant of something. That's right. Non-zero determinant of the Jacobian. Okay, so while I'm doing this, I want to think about what is the Jacobian going to be. In this case, so we want the determinant of the Jacobian of this guy to be not zero. So let's just see what this is. Jacobian of this okay, it's going to be a 3 by 3 matrix now. Okay, the first row is going to be determined by the gradient of whatever I put up here. And then the next 2 rows will be the gradient of this guy. So there's no dependence on x. And then I have, in this case, 2u1, 0, 0, 2u2. And of course, in a more general example, I could have more things here. Now there was a suggestion of let's put 0 here. That's the obvious first thing to try. The problem if I do that is that this row is going to be all zeros and I'm going to get a 0 determinant. So simple is good, but that's a little bit too simple because it kind of degenerates my determinant here. So that's not so good. So we have to go not quite as simple. We can't have a constant there. What's the next best thing to putting a constant here?
Identity mapping.
Yeah. Exactly. So if we put the identity mapping here, and all right, in this case, I just have one variable here, but in general, I'll have n, so I could write x1, x2, down to xn. It would be exactly the right number of components. And the Jacobian of this is beautiful, right? The Jacobian of this identity mapping is the identity matrix. In this case, I just get a 1 here. And when I try to take the determinant of this, it's just going to be 1 times whatever the U Jacobian was here. So more generally, right, let's create a function, phi, that is now square. It has the same number of inputs to outputs. Okay, and it's going to take this form. Okay, so the first n components are going to just be the n components of my x variables, right? The identity mapping applied to these x variables. All right, that's the right number of components to add in. And then everything else is going to be my original function. All right, this is still continuously differentiable. So our original thing was continuously differentiable. That means this guy is. So that's good. That's one thing we needed. And then the big thing that we were trying to check here was this Jacobian. So the Jacobian of phi. Okay, I'm going to do this, I guess, in a bit of a block form. So we start with these first equations, and we take the x Jacobian of everything over here. So x Jacobian of my identity mapping, the x Jacobian of my f, and then in the later columns, I have the u Jacobians of everything. All right, so what do we get? The x Jacobian of x is indeed just the identity. The identity is something that I like taking the determinant of, right? It's easy to take the determinant of, it's just 1. It's always non-zero. And we love multiplying the identity by things. So this is a really nice thing to have here. Over here we get zeros because x doesn't depend on u. Okay, and over here we just get our Jacobian of our original transformation. All right, now what happens when we take the determinant of this? Well, when we take the determinant of this, well, first row only has a single non-zero component, 1 in the first component. So that's the only piece that's going to show up in the determinant. Similarly, right, all we've got is a diagonal of 1s here. Everything else is 0. So when I take the determinant of this, what am I going to get? I'm going to get a whole bunch of 1s multiplied together times the determinant of whatever is sitting here. And this guy never actually shows up in the determinant because we've got zeros everywhere else. So the determinant of Jacobian of phi is actually identical to the determinant of the u Jacobian of f. And that is really good news because we happen to have as one of our hypotheses that this guy is not equal to 0. Okay, so the hypotheses that we have for this is precisely the hypotheses that will let us use inverse function theorem on this guy. So we can conclude phi satisfies all of the conditions required by the inverse function theorem. All right, so this is our mapping. Are we happy with this? Any questions here? So what is the rest of the proof? The rest of the proof is going to be looking through the things that we have to check. We have a list of a few things that we have to check, but all we're really going to do is say, what conclusions does the inverse function theorem tell us about this? And then we're going to translate that into what we actually want to be able to say. Okay, so let me draw a picture. Every good abstract proof should have a little picture to go along with it. All right, so what do we have? We have a point x, u, okay? We're living in this space with all our variables. The inverse function theorem is going to say that, well, we have some open set around here where things are nice. So we'll call that our set M. And when we take this brand new transformation that we wrote down, which recall was X and then F, what do we know? We know that's going to take, this neighborhood is going to get mapped to some new open set. Okay, so we'll have some new open set that I'll call M hat. Okay, and where do the points here map? Well, now again, we have n plus m components. The first components are going to be X again. And then the last components are going to be something that I'll call V. And what the inverse function theorem tells us is not only can we do this, can we take this open set, we can find an open set where this maps onto another open set, but we can go backwards. We have a uniquely defined inverse mapping that takes us back. So I'm going to call this inverse mapping gamma. So gamma takes these points, X and V, and it takes us back somehow. So again, we went from XU to XV. Now when we want to go back, we're going to go from XV to X and something. So the first components of our inverse map will be X again. And then the rest of the components are going to be something that depends on where we started. So just some function of X and V. Okay, so this is the conclusion of this is the picture version of the conclusion of the inverse function theorem. Okay, so the inverse function theorem tells us that this guy, this inverse function, is well defined on M hat. Okay, for some open set, for some open neighborhood of our reference point. Okay, so let's see what this looks like. Okay, so again, the first components are going to be X. The rest of the components are going to have some kind of dependence on X and V. So overall, there's going to exist some function H that takes all of these inputs and spits out something in Rm, takes us back to our U variables. And we're going to be able to write gamma in this form. So all the X variables, and then something that depends on everything, say X and V. Okay, and we know this is a nice function, right? Inverse function theorem tells us that this guy is, lovely and continuously differentiable. That means that this H function is continuously differentiable. So now what do I want to do? I want to use this to try to come up with a candidate for G. So right now I say that anywhere in this neighborhood of X and U in my full dimensional space, right? I have this extended mapping that takes us to this high dimensional space. And now I have an inverse function that goes from high dimensional space to high dimensional space, the square mapping. I'm not looking for a square mapping at the end of the day. I'm looking for a function G that has some particular properties. So I'm looking for a function G that, well, captures my reference point. And the big thing we wanted was to make sure that f equals 0. Now, so far, I've said nothing about f equaling 0 in particular. Okay, we just said that f takes us somewhere, not necessarily 0. We just want to find the points where f equals 0. Now we know at our reference point f equals 0, so we want to try to use this information, this gamma, or this h, to try to show that actually there's this function g that takes us back to the set of points where f equals 0. So this is what I really need to do. So we need a good candidate for g. And what's our goal? Our goal is to have that f of x and g of x equals 0. So the whole game, and this is how we're going to really prove almost all of the pieces that we need to prove, is to say, let's write down the thing we want. What we want is g of x. G of x is not living in the space that the inverse function theorem is talking about. The inverse function theorem is saying something about this full n plus m dimensional space. So I'm going to pair it with something. So on my left-hand side, I'm going to write the thing that I want, which is g, and I'm going to combine it with the extra variables that I need to get up to my full n plus m dimensional space. And now I'm going to try to see what does the inverse function theorem let me do with this. So again, this is the main thing that we're going to keep doing. We're going to say that the inverse function theorem takes a point of this form, right? And it lets us go back and forth. So we can go take this point, put it in phi, then we can put it in gamma, and we come back where we started. So that's what I'm going to do. I'm going to say this is the same as taking gamma of phi of this point. And now I'm going to put in, on one piece at a time, what is the form of phi, because we had a particular way that we defined phi. And then what is the form of gamma, because we had a particular form for gamma. So let's do this one piece at a time. So phi, we said, was x. X were these dummy variables that we added in. And then everything else was the function we actually cared about. Remember this guy, f is the guy we actually cared about, and he's what we used to define phi. And then these x variables were just our extra dummy variables to get the dimensions to work out. Now this looks complicated, but what we're hoping for is that this isn't some complicated function at the end of the day. We're looking for the points where this is exactly 0. That's the whole goal of g, to help us find the points where this is 0. So what we want, I'm not doing a rigorous proof at this point. I'm just trying to find a candidate for g that will then prove everything about. We're hoping is that this is true, that this can simplify to gamma of x and 0. And then I ask myself, well, what did gamma look like? Gamma also had a particular structure, right? It started with these dummy variables, right? Phi took my x points to just these dummy variables, which were x again. Gamma is going to take those x's back to the same x's. And then there was some other function here that depended on x, this variable, and it depended on v, this variable. In this case, we're particularly interested in not any v, right? The inverse function theorem tells us we can do things for a lot of different v's, right? Everything in the neighborhood of our reference point. I don't really care about all the different v's. I only care what happens right now when v equals 0. So I'm going to put a 0 here. And then if I compare my left-hand side and my right-hand side, all right, the first variables match up, so I haven't done anything too ridiculous here. And then if I looked at my next set of variables, it's suggesting to me that maybe g of x should be equal to h of x and 0, right? So again, we know the existence of this gamma function. We know that gamma has a particular structure in terms of these dummy variables, and then this extra function h. I don't know what h is explicitly, but I know it exists and it's nice. And this suggests that we should try g of x to be equal to h of x and 0. So I'll pause again. Are we happy with this as a good candidate for G? I haven't proved anything about G yet, but I've tried to at least motivate why this maybe is a good idea. And now we'll run through fairly quickly and try to check that G satisfies all the conditions that we want. All right, no complaints. I'm going to keep charging along. So what are the things that we need to check? We have this whole list of things that we need to check. All right, so I'm not going to do them necessarily in the order that I've written them here, but
Question.
Yes.
How can we match these two mappings? Their domains are different, right? Because H is from Rn plus M to Rm, right?
H is from Rn plus M to Rn. Yeah, that's right. So the first variables are these x variables, and now the key is that we haven't kept all the variables, right? We've set some of them just equal to 0.
But their domains are different dimensions, right?
G and H have domains that are different dimensions, that's right. Their range is the same dimension though, right?
Yeah.
So the key is that if I take any x, so x belongs to Rn, I think that's the way I had it, right? So given any x belonging to Rn, now if I just said give me any x belonging to Rn and also give me any v belonging to Rm, oh, I can't put all of that into G. That's too much, as you say. That's the wrong domain. But I'm not going to put any v in here. I'm going to put the 0 vector in here. So let's let 0 be the 0 vector in Rm. Right? This isn't going to depend on now, different choices of v. I fixed it, which means that I can compute this h of x0, which now also lives in Rm.
Oh, we want to show that the images are the same, not the functions.
It's that the images are the same. That's right. So this h function is not the same as this g function. You're absolutely right. This h is doing much more than I need. The key is that it lets me define a different function with the domain I need, and the images have the correct dimension. All right, so let's see what we want to check. One thing we needed to check was that we do the right thing at our reference point. Okay, so I'm going to actually do exactly the same thing that I did up here. I'm going to write down g of x naught, which is the thing I want to check, and I will augment it by these dummy variables, x naught, because this high-dimensional space is the space that's easy to work in because of the inverse function theorem, and then I'm going to, again, try to compare the appropriate components, the components I care about at the end. So if I start with what I want and throw in the dummy variables to go along with it, well, I've just defined g this way. X naught, h of x naught, 0. And this has precisely the form of my function gamma. Okay, we said gamma has, its first components are x, its second components are h. So this gives me gamma as long as I let x equal x naught and I let v equal 0. So this is exactly the structure of gamma, but just at this particular point. Now we have another name for gamma, for zero. Another name for zero is f at our particular reference point, right? We're hoping to find a collection of points where this is true. We don't know yet that we have, but we do definitely know. There's one thing we know is zero. The thing that we know is zero is, let me find out here. We know that f is zero at our reference point. So that's another name for zero. I want to bring an f in here. I'm motivated to bring an f in here because I'm trying to get everything in terms of my gamma and in terms of my phi. In order to get things in terms of phi, phi was defined in terms of f. Right? This is all I'm doing. I'm taking what I want and trying to put it in terms of gamma, put it in terms of phi. Okay, so we said another name for zero that we know is true is f at our reference point. And now we have something in here that has the structure of our phi function. We said our phi function has these dummy variables, x, and then the function f that we actually cared about. All right, so this thing inside gamma, this precisely agrees with phi as long as I take x equal x naught and u equal u naught. So this is gamma of phi at my reference point. All right, and what happens when I do gamma of phi?
Just like zero.
Exactly, they're the inverse of each other. So phi, I start with this point, phi takes me somewhere else, gamma takes me right back where I started. So this is nothing but x naught, u naught. And again, we know that this is a perfectly legitimate thing to do because the inverse function theorem told us there's a gamma that does this, that does precisely this. So now I compare my left-hand side and my right-hand side and say, all right, all the components need to match. So we've got equalities all the way through. So if all the components match, that means g of x naught is precisely u naught. So indeed, this function that we came up with does recover our reference point. So this was one of the things, probably the easiest thing we wanted to check, but the other things we want to check are not really any harder. So let me find that here. We've got this one accomplished. All right, let's see what else we can check. We wanted to check that this mapping we came up with, G, keeps us close to our reference point. So we wanted to stay in the neighborhood of our reference point. So maybe this is the next thing we'll check. Yeah, a lot of these things, it doesn't even matter that much what order you check them in. So let's check that x and g of x stay on our open set. All right, so what do we know? We know that our reference point, so at our reference point, x naught, g of x naught is going to take us to our m hat. Okay, so what are we talking about here? We've got our higher dimensional space. So where does phi take us? Phi is going to take some point here, x naught, u naught, take us into m hat. And what is u naught? What is f of u naught? F of u naught we know is going to give us 0. So we should be able to say that from the inverse function theorem, there exists some neighborhood n of x naught. Right? The inverse function theorem is going to give us this big neighborhood of both the x naught and the u naughts. So now let's just see what it lets us do with the x naughts. such that what's going to happen? Phi of x and our u's, g of x, is going to try to stay on this manifold whenever x belongs to n. Okay, so we have this mapping as long as things are nice, we stay close by. This is the inverse function theorem that says that we're going to stay close by. Let's say g of x naught actually. Now, what are we going to try to do? We're going to try to say that what happens to x and g of x. This is x and h. Right? And these are the points we're trying to check. Well, this has precisely the form of our gamma function. Okay, and what do we know about our gamma function? Our gamma function, let's find our picture. Our gamma function is going to take us back to our original manifold. Okay, our gamma function would do this for a much wider range of points, but in particular, it's going to do it for this point. So our gamma function is going to come back to our original manifold by the inverse function theorem. Right, again, it would do this for many other values of v, but in particular, it will do it for these values of v, for when we set v equals 0. So we're doing inverse function theorem with v equals 0. And that's what we want to show, that we go back to our original manifold. So this is, there it is, next thing checked off. Right, so again, here is a case where the inverse function theorem gives us more than we need. The inverse function theorem says I can take a whole neighborhood here and go back where I started. And we're going to say here, let's not take the whole neighborhood. Let's just restrict to the case v equals 0. And that still goes back to our original neighborhood. More than v equals 0 goes back to our original neighborhood, but in particular, v equals 0 goes back. Okay, so it's a technical lemma, but it tells us that, yes, we stay close by. Our g function is not going to try to suddenly run us far away from our original reference point. All right, what else do we want to check? The big thing that we cared about was that this g is giving us f equals 0. So let's try to check that. Okay, so again, I'm going to write down what I want. What I want is this object. This object only has m components to it. Inverse function theorem says I need to talk about a bigger space. So I'm going to augment it with my dummy variables again. Okay, so I have the thing I want augmented with extra variables to give it the right dimension. And then what do we want to do? We want to put things in terms of phi and put things in terms of gamma. This already looks a whole lot like phi, right? We said phi was, well, x and then f of xu. So this is phi, but with u replaced with g of x. And then we say, well, we had a particular way that we defined our G. It's here already. This is phi of x and h of x0. And then we look here and say, well, this looks familiar. X are dummy variables paired with h. That's our inverse function. That was gamma. Okay, so it's gamma where we take, well, x is x and v is equal to 0. So everything in here has the form of our gamma function with that particular choice of v. And once again, phi and gamma just undo each other. So we come right back to x0. And then I look up here and I say, well, all of these components have to match because we've got qualities everywhere. And that means in particular these last components have to match these last components. And we can conclude that indeed f of x and g of x is precisely equal to 0. So that was the big one. That was what we wanted to be true about our function g. We wanted to find a g that does this. And now we know that we did find a g, right? We took the inverse function theorem, which was this higher dimensional beast for us. But from that, we were able to identify a function with the correct range. Okay, and we gave it the correct domain by setting some of the variables to 0. And this thing that we have identified now does precisely what it wants. It gives us this family of solutions to f equals 0. So I can check that this is the case. What else? We want to know that this function is unique and continuously differentiable. Well, continuously differentiable is straightforward. Okay, why is it straightforward? Well, the inverse function theorem tells us that we have this inverse function gamma is continuously differentiable. Right? Gamma we wrote in terms of our dummy variables, and then this function h. So that meant that h is also continuously differentiable. All right, so this is true for a range of different values of v, but it will still be true if we fix v equal to 0, right? So all the partial derivatives of this with respect to x are nice, and they're continuous. Okay, and that will still be true in the particular case where we set v equal to 0. So we can say actually h of x0 is continuously differentiable. Right, because this point is contained in, it is our reference point. The point that gives us 0 is our reference point. So we've got a neighborhood where things are nice, so it's also going to be nice at our reference point. And this is exactly how we define G. So G is continuously differentiable. Okay, so we can say, check, this one is done. Now we also wanted to know G is unique. There's only one of them. Okay, so the next thing I want to check is what happens if there's two of these guys. Right, we always get uncomfortable in nature if we're solving problems and they have more than one different valid solution, because in reality, only one of these things is going to happen, and we want a model that picks up the thing that's going to really happen. So let us check, is G actually unique? Is there more than one way of defining this thing locally? Do you know what is the usual way of starting a uniqueness proof?
Pick two candidates and
Pick two
show that
candidates. Exactly. So every time you have to prove something is unique, almost without fail, the way you'll start is to say, let's suppose that we have G1 and G2 both work. So they both have all the properties that we've already shown to be the case. Okay, and now what we want to do is show that these guys actually have to be the same at the end of the day. Okay, I've got to, what do I have to do? I have to make use of my phi and gamma functions somehow, because those are the only things I can really say anything about with confidence. So G1 on its own or G2 on its own, I can't do anything with. That's too low dimensional. So I've always got to have it paired up with my dummy variables. All right, this on its own is maybe a little hard for me to work with. So let us pass it through this function that we do know something about. All right, so what does this function do? This function gives us, well, our dummy variables, and then it gives us f evaluated at this particular point, x and G1. Now, what have we assumed? We've assumed that G1 has all the properties that we've just shown, and in particular, if I stick G1 in here, f should give me 0. So this should give me x and 0. And if that's true, then what can I say? I can say that, well, I know how to undo this, right? What I want to get at is G1. So x, G1 of x, is going to be a gamma of all of this. Which is going to be gamma of my right-hand side. All right, and what was this? This was x and h of x 0. Okay, this is probably what we expected to get back. This is how we defined our G to begin with. Now the question was, did we have to define our G that way, or is there some more other way we could have defined our G that gives us this nice properties? But the inverse function theorem says, actually, because this gamma is, the unique inverse, actually when we compare things, we find that actually this G1 had to be h of x 0. There's no other option here. Okay. So before we just said h of x 0 is a candidate that we think is going to accomplish what we want. Now we've just said actually h is the only thing that accomplishes what we want. And now we make the same argument with G2. So we say similarly, right, phi of x and G2 of x is going to be x 0. And then we apply the inverse function, and we say that means that x and G2 of x is equal to x and h of x 0. So once again, G2 of x is h of x 0. But h is certainly uniquely defined, right? Our inverse function theorem told us there is a unique inverse function on this neighborhood, Okay, so that means H is uniquely defined. There can't be two different H's floating around. That means exactly that G1 must be identical to G2. H is uniquely defined by the inverse function theorem. So we can conclude that actually G1 is equal to G2. So we have uniqueness. Okay, so we say check. That was one of the other things that we needed. And we're almost done with this list here. We had a long list, but we're kind of trucking through here. There's one last thing we need to do. We need to work out the Jacobian of G here. All right, we're going to take the same approach that we did in the low-dimensional case. The low-dimensional case, we said, let's start with what we know. We know that f is supposed to be equal to 0. Now we can do implicit differentiation and see if we can try to extract the Jacobian of G from here. Okay, so this is our last thing to check. Okay, so we start with what we know. We've proved now that we have this nice neighborhood on which f of x and g of x is equal to 0. Now, we were given as a hypothesis that f is continuously differentiable. We've showed that g is continuously differentiable, so that means we're allowed to do the chain rule. Okay, I couldn't do the chain rule earlier because we do need to know that this is continuously differentiable, but now we're in business. So f and g are continuously differentiable. Okay, so that means the chain rule applies. All right, I have this composite function here that involves sticking g inside of f, but there's no problem doing this because our component functions behave themselves. So let me do this component-wise so that it's really clear what we have going on. So let's start with the ith component of f. Okay, so I'm going to write out all the inputs really explicitly. The ith component of f depends on x1 down to xn, and then it's going to be g1 of x down to gm of x. And we know that this is equal to 0. Okay, so now let's take a derivative. Let's differentiate with respect to xj. Okay, when I do that, well, I have to run through all the components here. Most of these first ones don't depend on xj. The only one that does is the jth component. So I'm going to get dfi by dxj, evaluated at x and g of x. Chain rule has me continue to run through here. Now, all of these g's do potentially depend on xj. So we need to run through all of these different g's. Okay, so I'm going to take the derivative of fi with respect to each one of these different components. So with respect to the ukth component, evaluated at the right place. And then the chain rule says, now I take the partial derivative of, well, the kth component of g with respect to the variable I actually care about here, xj. Okay, so that is the partial derivative of the left-hand side with respect to xj. The right-hand side is easy to differentiate. Derivative of 0 is 0. Okay, so let's see what we can pull out of this. What is this? This is running through the derivatives of fi with respect to all the different u variables. So in here, if I try to see what the sum is doing, I mean, we've seen this before, but I want it to be clear. This is looking at the ith component of f and taking its u gradient, and it's dotting it with, what are we running through here? We're running through all the different components of g and taking their partial derivative all with respect to xj. So what is this really? This is the ith component of the gradient of f, of the u gradient of f, dotted with the jth row of the Jacobian of g. Okay, that is a matrix multiplication. So this is going to be nothing but Jacobian of f times Jacobian of g in the ijth component. Now this similarly is our usual ijth component of the Jacobian of f, where we're only restricting to these x variables. So this guy right here is the usual way we write the ijth component of a Jacobian. And if I put this all together, what do I have? The x Jacobian of f plus the u Jacobian of f, evaluated at the place we want, times the Jacobian of g is equal to 0. Okay, and this is, all right, these are all matrices. So this is a matrix also, the 0 matrix. And now, what was our goal here? Our goal was to try to extract the Jacobian of g. So what I want to do is solve for the Jacobian of g here. The good news is that what is it pre-multiplied by? It's pre-multiplied by this matrix here, which is known to be an invertible matrix. Okay, so if I left multiply everything by the inverse of this, all of a sudden I'm going to be able to recover my Jacobian of g. So we know that by our assumption, this guy is indeed invertible. Right? Because we knew it was invertible at our reference point. We know that x and g of x keep us close to our reference point. We showed that. They stay in the right neighborhood. Okay. We know that this guy is continuous. Okay. So that means as long as we don't stray too far from our reference point, this is still going to be invertible. And all of a sudden we can write down that the Jacobian of g is, well, let's move this to the other side. It picks up a negative. Left multiply everything by the inverse of this. And all of a sudden I have a general expression for my Jacobian of g, of this function that I want. And in particular, I could plug in my reference point and work out exactly what this is. You know, in general, I don't know what g of x is, but at my reference point, I could certainly work out exactly what this is. So we have our Jacobian. So I go back to the theorem that I'm trying to prove, and I think this was the last item on our bucket list here. And we've got a full proof of the implicit function theorem now. So I'll pause a second. Any questions? You know, again, there were a lot of pieces to check, but most of it falls out very nicely from the inverse function theorem. We did most of the work for ourselves a couple of weeks ago. Okay, so let's do an example. Let's move from the abstract to the concrete. Let's suppose that I'm going to have a particular collection of variables, a particular transformation. Okay, and what we should expect here is that f should have the same size as u. And in particular, I'm going to give you this f. Okay, and then x squared plus z squared plus 2u minus v. All right, if I'm hoping to do any kind of implicit function theorem, I certainly need a reference point. So I'll give you a particular reference point that is 1 minus 1, 1, and 0, 2. And we can check. If we plug these in, what do we get? We get 2 plus 1 is 3, plus another 1 is 4, plus 0 minus 2 squared is 4, so we get a 0. Here we get 1 plus 1 is 2, plus 0 minus 2, 0 again. Okay, so this is a reference point that does what we're hoping it will do. It gives us 0. And now the question is, what can we get? What can we do with the implicit function theorem? Well, we should always, right, this is the warning, you always need to check that the theorem you want to use actually applies. Do the hypotheses hold? Okay, so what do we need? We need to know that f is continuously differentiable and that the u-Jacobian is non-singular. Well, we can work out all the different parts of the Jacobian. Here's the x-Jacobian. So we get 4x, 2y, 2z, 2x, 0, 2z. That looks continuous to me. So that guy we're not worried about. We have the u-Jacobian, 2u minus 2v, and 2 minus 1. Also looks continuous. And we care if this guy is invertible. So the main thing that we have to check is this invertible? So we check its determinant. The determinant of the u-Jacobian. Now, where do I care about it? I don't need to do this everywhere. I care what happens at the reference point. That's all that the implicit function theorem asks me to check. So at the reference point, what is this matrix going to be? At my reference point, u naught is 0, v naught is 2, then I have a 2 minus 1. The determinant of this is 8, which is certainly not 0, so we're in business here. So I can say great, f is indeed continuously differentiable. And the u-Jacobian is indeed invertible. Right? Always the first thing to check if you're going to use the implicit function theorem or any other theorem, do the hypotheses actually hold? Because we know that there are many examples of many results that we've seen where not every example is going to fit within the framework, but this one does. This one gives us everything we need. So we know by the implicit function theorem now that indeed there exists this function g. G takes all our x variables, so it takes R3 and spits out something that lives in our U space. It is defined near our reference point. Right? All of these results are local. And the big thing we want, f of x and g of x is equal to 0. All right, no idea what this function g is. It might be very complicated. Maybe in this example you can try to work out what it is, maybe not, I'm not sure. In general, certainly it might be very complicated. But the other thing that the implicit function theorem gives us is that this g in here is also continuously differentiable. And that means that since we're doing things locally, and we are only doing things locally, it's only defined locally, it may be very well approximated by its linearization. So since g we know is differentiable, we know that it is locally well approximated by its linearization. Again, it's the implicit function theorem that is going to let us do this. Okay, so let's see what we need in order to try to build up the linearization of this. The big thing that we need is the Jacobian. Okay, so let's try to build up the Jacobian. All right, so we already took the Jacobian of these different components of f. Now we've got them everywhere. We just need them at our reference point, and then we need to combine them in the right way. So the big one was this U Jacobian, which we said was 0 minus 4, 2 minus 1. We already computed that. And this part we need to invert. So if I invert this, at this particular point, you know, when you see these examples, you're never trying to do this inverse everywhere. It's always just at this particular reference point. What do we have here? Well, we said the determinant is 8. This is a 2 by 2 matrix. So the inverse is easy to write down. So 1 over the determinant. And then what do? We swap these two guys on the main diagonal. And then we do a sign flip on the off diagonal. And that's my U Jacobian. I need my X Jacobian, which again, we already worked out what it is up here. I just need to plug in my reference point. Okay, so where's my reference point? It's 1 minus 1, 1. Okay, so I'm going to get 4 minus 2, 2, and 2, 0, 2. Okay, there's all the building blocks we need for the Jacobian. So let's see, let's put it together. The Jacobian of G that we care about at our reference point is, okay, minus the inverse of the U matrix, Xi, times our X Jacobian. Okay, so let's see. If we do this, what do we get? We get minus 4 plus 8 is 4 up here. We get 2 plus 0. We get minus 2 plus 8 is 6. All right, minus 8 plus 0. Minus 2 is 4. And minus 4. Okay, so we know the Jacobian of G at our reference point. What else do we need to know? We need to know what G is at our reference point. Okay, again, inverse function theorem guarantees us that G at our reference point just gives us our U reference point. So G of x naught is going to be U naught. And now we're in business. I can write down this linearization. I can say, therefore, G of x is approximately equal to Gx naught, that's 0, 2, plus this matrix. Okay, and then times x minus x naught. Okay, so here my x has the 3 variables. X naught are these guys. So I'm going to have x minus 1, y plus 1, z minus 1. And now this we expect to be locally a really good approximation to this G that's guaranteed to exist. So this is going to get us at least very close to the family of solutions that we're interested in to f equals 0. And, you know, like we do with Newton's method, maybe you decide to iterate from there to try to improve your situation. So that is pretty much the implicit function theorem. Any questions on this example or on this result in general? All right, then, if not, from here, we're going to jump into chapter 7 next class and start talking about multiple integrals.